Thanks a lot, Jimmy, for the invitation. I'm Shayan. I'm a second year PhD student at Stanford. My research focuses on multimodal and spatial understanding and interactive editing. My advisor is Eero Arveni. This project is GuideFlow3D. It's a collaboration with Sinisha, who was previously at ENPS Paris Tech, now at Snap, and with Von Selectit, who is a professor at ENPS Paris Tech. This was the paper we presented at NeurIPS last month. The GuideFlow3D, an optimization guided rectified flow approach for appearance transfer. Now, before I even go into the details of what our method, let's try to answer the question, why 3D appearance transfer and why are we interested in it? So the main goal of 3D appearance transfer is that you would like to bring real world styles and material into design. So let's say if you walk around in your office or you see nice architecture, you would like to have the similar styles into a furniture that you have at your home. And the second point is you would like to generate 3D assets by transferring texture and fine geometry while preserving the shape. So, but that what I try to mean is that, let's say if you have this table at your home and you have the picture of a couch that you saw somewhere, can you get the table in the same way as a couch, right? Or if you would like to stylize a 3D asset, a 3D chair, 3D table in this case, with some text, and the text can describe a chair, text can describe any other object category as well. Can you still do it? So that's what I try to mean by saying generated 3D assets by transferring texture and fine geometry. The goal is essentially to accelerate stylized asset creation for gaming, AR, VR, and any digital prototyping applications. Now, in practice, 3D appearance transfer is quite hard. Let's look at why it is hard. So first is that different shapes or different furniture might have geometric irregularity, and absence of any sort of part-over grounding disrupt this texture alignment and the structural consistency. To give you an example, let's say you would like the chair here to get the texture of this chair. If you apply one of the previous methods, EasyText from SIGGRAPH 2024, what you get is another chair, but that does not really follow the correct texture alignment and structural consistency. You see this texture is breaking here, and you see these checkerboard-like patterns coming out here, which you've not really seen anywhere here. And also the legs are not really brown in this case, right? So basically, even similar shapes misalign with no structural awareness. These are two chairs, just very different chairs. So even similar shapes misalign without any structural awareness. And second is that when there are large semantic gaps across categories. So let's say if you want to transfer appearance from a chair to a table, I don't know, a giraffe to a chair, right? So this can break correspondence and cause style leakage, and thus producing textures that fail to align with the object geometry. To give you an example, so let's say if you have this table on the left, and this you would like to have the same texture and the same appearance as this chair. What you get with Trellis, maybe a few of you are familiar with Trellis, which is a 3D generative method released by Microsoft last year. Now they also have Trellis 2, but Trellis 2 was just released. So this is a 3D generative method, and what happens is that there is no semantic correspondence here. So different shapes collapse when style overpowers the structure. And our goal is can we solve this problem using without doing a lot of retraining, because not everybody has compute, and not all the time you would like to retrain a generative method for this sort of algorithms, right? So our solution is that guided flow for appearance transfer. So what we do is that, let's say if you have an input 3D mesh, which is input 3D mesh, and we basically introduce differentiable guidance during the sampling process. So if you're familiar with universal diffusion guidance, which is basically when you are trying to sample from the latent space of when you do the sampling in a diffusion model, what you do is you try to sample for n number of steps. And what we do is that you sample one step and then you run our optimization. And by interleaving this rectified flow sampling and the semantic and the geometric prior as the guidance objective, our whole goal is that we would like to get style final output, which is much more closer and much more relevant to what you have actually asked for. The main question here becomes is that how do we formulate these guidance objectives which enforce the semantic and geometric consistency? So we essentially develop two types of guidance. So first, I will talk about part-aware semantic guidance, and then I'll talk about another sort of guidance so that you can have multiple modalities as input. So let's say if you have an input 3D mesh on like this chair on the left, and this is your appearance object that you're trying to take the style from or the appearance from. What we do is that we introduce this guidance to a diffusion model. So let's say you have a pre-trained rectified flow model. In our case, we use Trellis as our base model. So what we do is we introduce this L appearance or appearance guidance, which takes in this input 3D mesh, the appearance object, and the reference conditioned image, if there are images available. Then it runs one step of sampling from the flow transformer and one step of guidance. So essentially, how we do this guidance, you can think of it in multiple ways, but very simply, what we try to enforce here is that. Let's say we have this chair, we have this chair and these two chairs. We use a part field. We use part field, which is a part segmentation algorithm, to get some feature points for every voxel or every point in this mesh. And then what we are trying to say is that the similar parts so the back of this chair should correspond to the back of this chair. The seat of this chair should correspond to the seat of this chair. But as you can see here is that this part co-segmentation or co-segmentation is not really always correct. Here, if you see that this is red, while the on the back, but the red is here only on the legs. And what we are trying to enforce here is that we do a soft assignment with co-segmentation clustering to enforce that this guidance that we are providing is basically trying to tell the optimization algorithm that, okay, look, these two chairs have these are the similar parts. So you should take the appearance from this part of chair A and put it to this part of chair B. So that is how essentially it works. And we match this input and appearance latents through part-based co-segmentation, which is what I just explained to you. And once we have this have this happen in the latent space, what we do is we take that latent space, we push it out to a decoder, and our decoder should be able to support mesh radiance field or a Gaussian splat. And then what you get as output is this chair stylized in the same appearance as this chair. Right. Now, you might have a question is that, okay, what if I do not have an appearance object available? I only have an image, or if I just have a text available, you cannot really use this sort of guidance. So what do you do in that case? So here we introduce another form of guidance which we named self-similarity guidance. So here the idea is also very similar, is that you have this input 3D object, which is the chair. And then what you do is that what we try to enforce here instead is that we do geometric clustering. By this, what I mean is that we do take, in this case, we take part field features, but you can take any sort of 3D feature. So this is not really relevant, just for using part field features. You can take any 3D features. We do have some ablation in the paper. If you're more interested, that we can work it out with other features as well. So here, what we are trying to enforce is that the positive part, so all the features of all points in this red part or in the seat should correspond to each other and should be different from all features of all points in the back. So here this is how we try to enforce self-similarity guidance. Again, so we do one step of sampling and one step of optimization, and that is how we try to enforce guidance in this case. And then once we have this, we again use a decoder to just decode it out to whatever 3D representation that you are most familiar with. Right. So how does this help is that how is this approach or guidance is helping in this case is that you are sort of able to promote local consistency, because we have this thing that we have positive parts and the negative parts. So you can promote this local consistency. So that's the intra-part, intra-part similarity without homogenizing the appearance globally, because we still have these positive and negative part concept. So you get both local consistency and no global appearance homogenization. So that is how we enforce guidance in these two cases. Now, there might be a question in your mind is that, okay, you have introduced guidance. There is universal diffusion guidance already. So you've introduced guidance in this way. But does this guidance help make a 3D pre-trained model like Trellis, which is a 3D generative model, like you can do image to 3D or text to 3D with this model? Can you actually use it for this task, even though you have some guidance which is completely for a different task? Now, how does this guiding the structured latents or these latent space helps in this case? So let's say you have this appearance object, which is a chair. So this is, let's say, the image that you are looking at. So without rectified flows, let's say we just had guidance. So we did not have any pre-trained model. So this is just pure optimization. What you get is, you can see is that this is not really consistent, right? You get these texture breakage, texture getting leaked. You get the flattening of texture on the corners, right? And without guidance, you can get a much more plausible result. That's because when you use just an optimization, your model can just, the optimization strategy can just make you fall off the data manifold, right? But when you use a rectified flow model or any generative model in this case, you get a much more plausible. But you can see still is that here there is style leakage. Like you can see that the chair's legs style, like this black part is leaking into the seat. And you can see this part where you have extreme texture flattening. Right. Now with GuideFlow3D, what you get is you do not get these leaks anymore. And instead you get an appearance which is much closer to the actual appearance object that we started with. So we essentially try to go from plausible shapes to semantically grounded textures. Like if you look at the final output with GuideFlow3D, what we are trying to put here is that you get textures that are semantically grounded. So you do not get the texture of, the leg of a chair on the seat of a chair. Like that's something we shouldn't get in this case, right? Now, let me show you a few visualizations before we go more into what applications this can unlock and how do we perform compared to other baseline methods. So essentially, in our paper also, we show results with multiple ideas. So here is that we show results intra-category with the image. So essentially, you have an input 3D mesh and you have an appearance image. Both are of the same category. So these are both two chairs, just not the same chairs. One of them is more of a work chair. One of them is more of a chair that you would have lying around in your kitchen or in your dining rooms, right? So we do compare against multiple baselines here or multiple previous methods. So first we devise a very naive UV nearest neighbor approach. So where we're just trying to put the text, we take the texture map of this asset, and we are just saying that, okay, if these 2 points are the nearest to each other in these two meshes, just put the U texture map next to each other, and this is the easiest baseline we could think of. And then as you go around, the difficulty of baselines keep increasing. So then we have Mamba-ST and cross-image attention, which are 2D based methods. What we do is we do this texture or appearance transfer in 2D, and then we lift it to 3D with a 3D generative method. And then you have EasyText and Trellis, which are 3D style transfer methods or both 3D methods, right? And then you have GuideFlow3D. So if you look at what happens is that the 2D UV nearest neighbor, Mamba-ST, or cross-image attention completely misses. There is a lot of sims, there's a lot of artifacts. EasyText has this issue that it produces inconsistent textures where the handle of the chair is not really consistent. Like since the handle is not present in the appearance image, it is putting basically garbage in there. With Trellis, since it's a quite a powerful pre-trained method, and that's the base model that we are using, you get quite impressive results. But what is still failing is that your the seats, the handles here are not really consistent. But as you apply guidance on top of Trellis, you get this guidance very nicely. And then what you essentially get is you are able to transfer these fine-grained textures while preserving part consistency. So there is no mismatch in in textures getting transferred between one part or the other. And you also get enough shape fidelity so that you get these high quality textures getting transferred seamlessly, right? But you can say that, oh, Chan, intercategory is a very easy solution to work with. Can you actually do like intercategory? Can you do a chair to a table, right? But before that, I would also introduce intracategory with text. So here, if you have a wooden cabinet, and now you would like to have the appearance text, right? So which is just defined as text. So can you really stylize this 3D mesh based on the text that appears? And as you see with UV nearest neighbor or SDXL plus cross image attention. So what you do is in this, we devise a baseline with cross image attention and then do the transfer using SDXL, which is the stable diffusion XL part. And when we also have Trellis doing it. Now, if you look at a trellis, it's not really producing a reddish brown rectangular wooden cabinet, right? The color is still missing. So that is what we pick up. So UV nearest neighbor and SDXL cross image attention baselines fail miserably, but trellis is producing a cabinet, but it's producing a wooden cabinet, but it is not really able to pick up that reddish brown texture. And that sort of fine-grained control is what our method is all about. So we are able to align these text-based appearance with both object structure and semantics. Okay, now that I have talked entirely about intra-category, let's look at how you could go from a chair to a table. And maybe I will show you more diverse use cases as well. Right, so let's say if you have this table, right? Input 3D mesh, which is a table, and then you have this as a cabinet, right? This can be as a small cabinet. So how does it look? So what happens is that, yeah, this is where trellis starts falling off. So UV nearest neighbor, Mamba ST, all the other baselines, they were already falling off before because they were not able to have the correct sims. But in this case, trellis also falls off. Like it just produces some random texture, which is basically a random texture on the part which is not really there in this appearance image. This happens because that trellis is not really doing any part-aware grounding like us. So what we do is that you sort of get the same top, and you get the same color on the other parts of this table. Right. So we are able to sort of generalize across category, and we do maintain realistic materials, and we do maintain the structure. We do not really have any problems in maintaining the structure like some of the other methods that you see here. Right. Okay, now that we have pushed it to intercategory with image, can we push it to intercategory with text? And just to take a bit of a zoom out here is that intercategory with text is basically very abstract. So essentially, if you have an input 3D mesh, which is a chair, and you have an appearance text, which is essentially of a coffee table. So essentially what you're trying to ask the model or trying to do stylization here is a very abstract semantics. Like you're trying to put the appearance of a table which is defined with text into a chair. Can this really work out? So what we realize here is that, okay, UV nearest neighbor and SDXL, they do produce good results. Is that UV nearest neighbor result in this case is one of my favorite results because it's extremely visually appealing, but it doesn't follow the prompt at all, but it is visually appealing. So with trellis, what happens is that you get sort of very blurred version of the texture that you're looking for. I mean, it does happen, right? But what you don't get here is the fine-grained detail. Again, you do not get these thick, black, tapered legs, right? So you just get the light rectangular coffee table with 3 plank tops. So what it probably does is that it produces all over the place a wooden texture, right? But GuideFlow3D, using the same base model as Trellis, just by introducing this training-free guidance, is able to recover it into exactly the appearance text that you described. So we can generalize across category, not only from image, which is much more, which gives you much more signals, but we are also able to do it from abstract textual cues. Right. Now that I've shown you a few results, let's look into some of the evaluations here, right? So with quantitative evaluation in style transfer or appearance transfer, especially in 3D, is extremely difficult to do because there is no ground truth. What most papers have been reporting before us is that there are these perceptual similarity, dream clip scores, dream sim scores, like all these perceptual similarity scores. We do report all these in the paper, but we believe that this is not where your evaluation should be, because it's very difficult to get ground truth for these. So what we do is we run an evaluation with an LLM-based evaluation and a user study with 1,000 participants to tell us that whether what we are looking at is actually correct, or whether what we get is complete bullshit. So what we get is that LLM rankings rankings align with human preference, confirming the superior appearance transfer quality that I have been showing you for the last 4 slides at this point. Right. So what we do is that we take the output, we take the input, we render it into multiple views and pass it to an LLM or give it to a human rater to ask saying that, okay, I rank it on a scale of 1 to 6, or rank it as which one is better. We see that GuideFlow3D does have an extremely high win rate, or a preference rank of average preference rank of below 2 on a scale of 6 in with an LLM. If you are more interested in the perceptual similarity results, do feel free to check out the paper. Right. So now I have talked about quantitative evaluation. I have shown you results. Now, for the last few minutes of my talk, let's look at some of what are the applications of this approach. So the application is that one application that was pretty cool was this is one of the coolest results that I saw, is that can we do in the wild appearance transfer? So can we have this bike in the texture of the chair? Can we have this chair in the texture of a giraffe? Can we have this plane in the texture of a cabinet? So as it turns out, without any retraining or without tuning any parameters, GuideFlow3D is able to handle these cases. And this just shows how easily, with our guidance approach, is that you are able to do generalization, and you're able to have this quite out of category, cross category in transfers. Another application which I'm very personally interested in, because I'm from a 3D background, is scene editing. As in, let's say if you have an input scene. So this is a scene, maybe some of you recognize this scene from ScanNet, which is I think a de facto 3D dataset, a 3D Indo dataset at this point. What we do is we take an input 3D scene, we run an off-the-shelf object pose estimator, bounding box detector, and get meshes for every object in that scene. So you can see the chairs in green, the tables in blue, these things in tables in pink, and these things in blue. Now that you have this appearance objects, the idea is that can you stylize them, or can you have appearance transfer of a different object in this case? So what we do is that we try to restyle the chairs in the style of the sofa, the table in the style of this table, and the garbage bin here in the style of this cabinet. And then what you get at the end is that you sort of get interactive 3D scene editing, where you can restyle your scenes with context-aware transfer. And I think this is a very cool application that you can directly do with this sort of a training-free approach, right? So these are the two applications we are quite interested in. And there could be much other applications as well, but these were the ones that we explored while doing this project. Now I have talked about applications, I have talked about the results, and I have shown you that GuideFlow3D is sort of quite a good approach to do this 3D appearance transfer. But is it all roses? Do we not fail? That's not the case. We do fail. And where do we still fail? So let's say if you have an input 3D mesh and you have an appearance image, which is this. So let's say if you have this table and you have this combination image where you have a table, a chair, right? So what happens is that trellis fails completely. And since the base model completely fails, we are able to recover. So if you still look at it, we're able to recover, but we are not able to get anywhere closer to the texture that you have here. So essentially, what I'm trying to tell you here is that interpreting abstract semantics without ambiguity still remains a very open challenge in this quest. And that's something I would like to see future work coming out in this direction, if any one of you is interested. So the key takeaways from the last 25 minutes of my talk is that I did present a novel framework for 3D appearance transfer that tries to apply universal differentiable guidance to a pretrained rectified flow model. We have a training-free approach which generalizes to different appearance representations. Like you can use a mesh, you can use an image, you can use a text. So whatever 3D representation or 2D representation or 1D representation you are most familiar with. And our whole goal is that we want to bring control level creativity to 3D generative design. The 3D generative design shouldn't feel like a black box. So this is bring this control level creativity, and you can get this fine grained control. The few future directions that I am personally also very interested in is that since this is a guidance-based method and we do optimization during inference, right? So this is test time optimization. This is not quite fast. So we do add a bit of overhead on top of the method that we have, right? On top of the generative method that we have. So can we train a self-supervised model for a fast, efficient inference? Now, and the second is that can we, in principle, extend these guidance objectives to other tasks such as 3D reconstruction? Because in this case, I only showed you how implicit guidance in the latent space would look like. But can we do both? Can we do a combination of both implicit and explicit guidance to do 3D reconstruction, like a 3D object reconstruction or 3D scene reconstruction? So these are the future directions if that could potentially span out from this project. And with that, I sort of end my talk today. Thank you for hosting me. If you have, there is the project page link here. The code is still there is a code on the dev branch of the repo, but we do have a demo and there are slides, and we do try out our Hugging Face demo. There's a